So yeah, today we're gonna break the Enigma. Let's get right into it. So first, so you know a bit of who am I. I'm an astrophysicist and computer engineering. So I'm currently working as a software developer at deciphering, great company. Well, I'm not doing that. I really like doing art, especially pottery. So if you want to talk about that after, I'm in. And I have a crush on cryptography. So luckily, our previous speaker already put us in the mood of security and breaking codes and things. Let's do that, but in the cryptography side. So let's start with us, with humans. This is very natural. When we talk to someone, we don't want anybody that is not in the conversation to hear what we're saying. We put our password in our bank, and we don't want anybody else to know what it is. We need these secure channels of communication, and that has been the case since forever. So we can go before Christ and see examples of ciphers, people trying to take information and transform it somehow, send it on the clear so no one understands, and then the person that gets it and has the key or a way to decipher it can read it. So we can see, for example, Julius Caesar. He used to talk with his generals via ciphers. We know the Caesar cipher is very simple. You just take a letter and move it, assign it to a different letter of the alphabet. So an A becomes an X, a B a Y, and so on. And he sent messages like this. So to the bare eye, someone that just sees this is like, this is just gibberish. Well, it says hello PyCon there. But this is very simple to break. With time, you start doing some techniques, some analysis of language, and in the end, you break it. So right now, we use things a lot more secure. So for Bitcoin, for example, cryptocurrencies need a lot of security. So Bitcoin uses algorithms like elliptic curve and public and private key schemas to keep everything secure. And it's very hard to crack. So I want us to locate ourselves somewhere in between. This is 2020, this is before Christ. I want us to be in 1939, 1945. These are the times of the Second World War. And I chose this example because we see every day how technology shapes history, the world we live in. This is an example of how history shaped technology and how everything that was going around, well, created this advance in cryptography. Yes. So imagine you have a machine. An Enigma machine is something like this. It's not very big. It's a small machine. And whenever you wanted to send a message, you type it in the machine. And the machine turns you something like this. Something, again, we don't really know what that is. And you send it via clear. You send it on radio, Morse code, whatever you want. And anyone else, all of the other generals or outposts that had the machine, type it in and get the initial message back. So it's cool because it's symmetric. Whatever you input, if you input it again with the same configuration, you're going to get the initial result. So, the machine looks something like this. Imagine a typewriter, like one of those old typewriters. Whenever you type a letter, there's an electrical signal that's going to go through something called the blackboard. Then it's going to come to some mechanical mechanism called the rotors and some reflector, and it's going to come back. Just the electrical signal is going to travel back to the lamp board. So whenever you type a key, another letter is going to light up. So something interesting, if you remember the Caesar cipher, an A was always transformed to an X. But here, the person is typing the same letter and is getting a different light every time. So when you see the message, you cannot apply these old techniques of language we applied in the Caesar cipher. This is going to be a bit more complicated. The secret about the machine, the way that you would actually decipher the message, you would think, okay, we need, another machine. But the machine was not the secret. Everyone knew how it worked. Everyone knew what it was. The secret was what was the initial configuration of these things when you put it in. You see that it's spinning? So in which position you put it at first, and which one do you put in which order to, actually cipher things. This was also the secret, and the reflector you put in here. So like the components that you put are going to be what's going to be shared among, the high secrecy communication. So this looks something like this. It's very big, but you can just see that every single day they had a different code. The secret changed. Even if you were able to crack the code today, the next day it was going to be a thing completely different. And it has this super giant configuration. I like to show this because there's a nice story how the Navy was really jealous about their codes. They didn't want them to be a liability. So they actually printed these things in solvable ink. So if whenever a ship went down the water, this was going to solve away. So they were really secret. You can see here it's declassified right now. So all of that sums up to something like 10 to the 25 combinations. This is 62 septillion combinations. We cannot even imagine this number. So just to put an example, the universe, the entire universe we watch, the observable universe, is 800 septillion meters. So 62 septillion combinations is a lot. They were not going to be able in one day to just try them all and see, oh, okay, I found it. Maybe if they were lucky one day, but this is not the way of solving the cipher. So how do you do it? At the time, this thing was thought to be unbreakable. No one had any idea. So you assemble a team, something like the Avengers, and you put mathematicians and you put different, engineers, people from the military, everyone else to think. So to try to find something, that will give us the back door. Something like we saw in the previous one, just finding these small flaws is going to help us. And there was one. From those 62 septillion, there was one single flaw. So do you remember that every time you type a key, something different lights up? Well, it turns out that it's never going to light up the same letter you type. So if you type a K, you're never going to get a K. And this was huge. This doesn't seem like much, but that was the single reason of why the Enigma machine was cracked at the time. So you add up some math, and you put in some technology as well, and you get something called the Bombe. So this is a huge machine. You can see it to scale here. And they used to run this every single day to crack the code of the Enigma. So how did they do it? Right? That's the question. That's the title of the talk. How do we break the Enigma? I'm going to walk you through an overview of the steps they took. So we have a message. This is what we get. We hear it on the radio. And we're like, OK, what to do? Let's think that there might be a word that appears there. You know that whatever they're talking about, you know the topic, you know what it's related. So you guess, you make a guess. You say, I'm going to suppose that this, not word, this small sentence appears here. And I'm going to use the flaw to see what can I get from it. So you know where it is, that it is there, but you suppose. But where exactly in the text? Why do you actually want to do this? Is because in cryptography, you always want to have these pairs of cipher and unciphered text so that you can, play around. So you start sliding it. You start saying, OK, let's assume it's at the beginning. So this would be the translation of attack at dawn. But here, an A, it's an A. So it cannot be there. So you move it a little bit, and you're like, OK, no, again, A, it's an A. You keep moving it, and you find something that's possible. So this could be, we don't know, this could be the location of that message, of that small text in the word. And you keep doing it, you find another one, and you gather all of these ones. All of this pair of Crips. They're called Crips, sorry, I didn't mention that. And they used to do it by hand. They took a little piece of paper and they just slide it around the message and find whatever things don't match or match. Then you have it. You have your pair, you're kind of confident. It's still a probability, but you think it is. And what's cool about it is that you have, whatever the setting was in the machine, you have a consecutive steps of translation. So you already have an insight inside. So Turing and all of his team transformed this into something like a state machine. So I don't know if you ever saw this in classes, but it's basically how you move from one state to another one, and in which order you do it. So you move from an A to a W, or you move from a T to an S, and you do it sequentially. These menus, these graphs, would be an analogy of what we will call today a program. It's what you would input into that machine to run. And just as another requirement, you want this graph to have the most amount of cycles inside, and also the most amount of nodes. This is actually a drawing, one of Alan Turing's notebooks. They drew everything by hand. So he was just like sketching and finding the best kind of menu he could find. And then the hardest part. So how do you input this into the Bombe? So one of the million reasons why Turing was so amazing is that he was able to program. I'm going to show you a real picture of this, but he was able to find a way to program a machine where computers did not exist, these things didn't even have memory to work with, and make mathematical deductions on it. So deduce somehow how to reduce all of the number of possibilities. So this is not moving. Sorry. Okay. So ideally what it does is you guess that your machine has some initial configuration. You guessed it right out of randomly. Then you guess again another plug-board connections, one of the ones below. And somehow you deduce, using your map, what is going to be the next letter. Then if you ever get some inconsistency, something that doesn't match, then all of the previous guesses you have are wrong. I don't want you to actually understand all the mathematical deductions on it. I just wanted to show that by making some assumptions and finding some inconsistency, you can remove millions of possibilities of the ones we checked before. So what he did, we could say, he had a lot of smart Enigma machines all running in parallel. So he was already doing parallelism, concurrency. And every time you find something that doesn't match, then you update everyone and you tell, OK, stop checking this configuration. Let's move to the next one. And this happened very fast. So this is an image of the machine. You can see on the inside, it's incredibly complicated, nothing like laptops we have today. And they actually dismantled all of this during the war. So this was a reconstruction of it. That's why it's in color. And it used to run for hours trying to find the solution. So finally, once you run it, you could get different outputs that match your text. There might be different configurations that could be similar to what you have. So you have some false positives, some stops of the machine. So what you want to do is, well, just find the true one. You have your message, and you just pass it to all the selected configurations that you found. So you try with the first one. And again, you translate it. You use the code. And you see that you get the word you wanted, but all of the rest is gibberish. You don't really understand what it says. So you try with the next one, and then you try with the next one, and then one of them actually makes sense. So on December 8th, attack at dawn. And then you found your code. So all of this process involved a huge human effort. You had to find all different Crips to make so many guesses, to find the menu, to draw these graphs, and then finally just analyze tons of possible false positives that you would get. So now we come to why we're here. What would have happened if we could do all of this they did with the computer, with the technology we have now? What if particularly Turing and everyone actually that was at Bletchley Park at this gathering of really smart people, what if they had had Python? So let's try recreating everything with it. First, we start with Enigma. So it's pretty simple, some initial configuration, some input text, we process it, and we get the cipher output. This, in Python, I'm going to show you code after. This one was not really worth it, but this takes around 0.6 milliseconds. So pretty fast. We're already beating someone that's typing it. Could we do a brute force attack? Like, could we just try all of them and let this run? Not really. This is still like very high time, and we would need a very specific architecture. And I wanted to recreate this myself, in my laptop, in my computer, like what a normal person could do if they wanted to crack Enigma. So let's use the flow. Let's do what they did. Let's start by getting all of our possible Crips, all of the words that might appear, and try to put them here. So first one, we go through all of the possible words, and we just slice it. Slice the message, basic string manipulation. We compare them. If all of the words are different, then all of the letters are different, we add it to our list. So we get a list of Crips. This takes around 3 milliseconds. This sliding and taking a little piece of paper and going through all of the messages and then trying with different words, 3 milliseconds. So good, we're advancing. Next one, it was finding the menu. So how to convert every single pair that you found into these kinds of graphs. So you go through all of the possible words, all of the possible Crips, and you create some graphs. For graphs, we have structures like dictionaries that are very high performant. We can have direct access, so we just save information there. And now we have algorithms, like graph algorithms, that could help us find those cycles, to score these graphs to find the best one we want. We could use depth search first. These things were not invented, but they were just, during that time, they were figuring them out. So not even graph algorithms existed at the moment. So this, for let's say 500 words we have, 500 possible Crips, takes about 25 milliseconds. Now doing the hardest part, the running the bomb. In here we have to make some assumptions to not fall in not let historical accuracy run us over. But let's try to see how this would look if we coded. So first, we start making our guesses. And we go through all of the possible paths of our graphs to find them. Well, to run them, sorry. So we run multiple Enigmas at a time. We load them with different configs. We could use libraries right now as multi-threading, or just whatever you want to use in Python to have concurrency, and run all these smart Enigmas in parallel. Then you do all the math deductions. It's just a bunch of nested ifs, so your complexity doesn't get very big. And finally, you add all of the candidates that could solve it, like we saw before. So this, for the example we've been talking about, takes about 5 minutes running. On an average laptop, a person could get with very standard Python. And finally, we need to analyze the result, the last part of the process. So for all of the possible settings we find, we load our Enigmas and we encrypt the whole message to see which one makes sense. How do you know if you have thousands of different deciphers, which one makes sense? We read it because there were just 3, but how do you find that text and see this actually says something? Or is just letters scrambled around? Well, we have dictionaries. We could detect how many matches do we have to language words. We could also do word frequency analysis, tokenize our messages. We could use even natural language processing right now to analyze the text and to find the perplexity, how meaningful it actually is. So I want us to compare for them and for Python. So finding a Crip, it took them around 20 minutes. This is based on literature and books of estimation, rough estimation. Every day was different. But Python does it in 3 milliseconds. We want to find a menu, these graphs, around 1 hour, to finding the best one, to draw all of them, to see which one is the most ideal. 25 milliseconds. Running all of them, this is like a very, very large improvement. Then running the bomb. This was the longest one. This took about 2 to 4 hours. A nice story here is that they had around 50 bombs, 50 of these machines in the UK. And in the US, they had around 150. So they asked the US for help, like, hey, can you run this? So they had copper wires that went down the ocean to the United States, and they sent the menus, the programs. And then the US run them and bring them back. So we can see one of the first examples of sending your program to the cloud and getting a reply. But this took them around 2 to 4 hours. So we do it in 5 minutes. And the final part, the analyzing the results, and here you actually have tons of people to help you. It took you about 30 minutes, and people that knew German as well. So you have a level of extra complexity. And we could do it in around 2 minutes. So less than 10 minutes, everything that they took them around 6 hours, maybe 5 to 6 hours. So it is a huge, huge improvement. And I know I threw a lot at you today. It is very complicated. I didn't want you to actually go outside and crack the Enigma, come back. We can talk about it because all the code is available. I'm happy to share it. I just wanted to show you how these kinds of problems, these kinds of secrets and messages that we weren't able to understand can drive technology forward. So let's see what they did. The first thing, well, is that crypto makes our technology evolve. These people, all of this group of smart people created, arguably, the first computer to solve a cipher. And right now we're having quantum computing. We're literally asking physics itself to help us, well, just solve programs. The next one is that we need different ways of thinking. A brute force attack was never going to work. And they actually brought people from a lot of different backgrounds. So this is again an example of how diversity helps in our teams. How having someone that knows math, having someone that knows maybe a strategy, some psychologists, people from languages, how having people that think different and seeing problems from a different perspective can help us, well, solve them. And the last one is that design flaws become exploits. So everyone the person that created the machine should have thought better, should have seen this coming. And we see this in software every day. We sometimes get run over by time and we sacrifice quality, and the more time it passes, the more that design flaw is going to affect, well, your software or anything you do. So I didn't want to finish on this complicated note. I just wanted to show that Python works for something different, something, well, in this case, security, specifically cryptography. And this was a very historical example, but we could do a lot of fun things now. So I'm going to send you a message, myself. And I want to see if someone knows how to crack it. So any idea? What did I just said to you? Well, this is an audio. So let's think. Let's do our ideation session. So what could we do with audio? Like what could I have sent you? Maybe it could be cipher. I could just run it through some type of encoding, different encoding. Maybe we can visualize it. I don't know if you had, for the people who had Windows, the reproducer when it draws things when you're seeing a song, when you're listening to a song. So maybe we could do something called a spectrogram. It's when you have time and you plot the frequencies you're hearing. So let's try it out. We have libraries in Python for plotting. We have libraries in Python to read audios. Let's see what we get. So this is time and this is frequency. Does it look familiar? Maybe. So we can hide information. I was not able because it was at the same time, but there's another talk by Manuel showing how we can hide data inside data. This is not specifically cryptography, it's called steganography, but another branch of security of how we can hide things inside other things that for the bare eye, for the bare ear in this case, don't mean anything. So finally, as a big conclusion, I am a firm believer that tools are a big part of what makes us human. It's what differentiates us from other species. It's what makes things easier and proper. So it's how we use those tools that really matter. What they did in hours, 5-6 hours, we're doing it right now in less than 10 minutes. So what could we do with Python now? What ciphers could we crack? We saw the previous speaker breaking our Air Force site, but well, the ethical part is also very important. But what else could we do? What new ciphers we could come up with? We could break. It's the tool the tool's power. So thank you, and I welcome all the questions.